Okay, so now we're going to talk about activators. Activators bind to DNA and they'll recruit RNA polymerase to a nearby promoter site. And the question that we want to ask is, what is the probability that a polymerase P is bound in the presence of an activator A, given an interaction epsilon AP between them? Okay, to find this probability, call it PB, we need to calculate the partition function Z. So the total partition function Z is a function of P, the number of polymerase, A, the number of activators, and N, the number of nonspecific DNA sites. Okay, and the total partition function is equal to Z of P and A when there is an empty promoter site and an empty activator site, that's this scenario on the top, plus the partition function when a polymerase is bound with specific energy epsilon PDS. Now there's pol 2 specifically bound, that's that scenario, the second scenario, plus the partition function when just an activator is bound to its specific site, plus the partition function when both pol 2 and the activator are specifically bound, which get their corresponding specific energies plus an interaction energy epsilon AP. So that's where both pol 2 and activator are specifically bound and interacting with each other. And that's this bottom scenario that's circled here, which shows both polymerase and activator bound and interacting. Okay, and the partition function, as we've seen before, can be written as a combinatorial expression involving those factorials, and you can see that pictorially in the picture there, times a Boltzmann factor with a nonspecific energy of binding P polymerase and A activators. Now, the system is approximated to be dilute, so that P and A are much less than the total number of nonspecific sites, and then we've seen that factorial function simplify, as I had written there, so that the partition function can be written in that simplified form. Okay, and here's where I'm going to segue this tutorial into the description that I gave last year. So we left off last time by writing the total partition function for a system that consisted of both polymerase and activators of polymerase on DNA in a bacterium. So this is a very simple model of gene regulation of how an activator can assist in the expression of a gene. And we can understand that, how we can understand that statistical mechanically. And so we start by writing the partition function, which you can see here consists of 4 terms. I don't know if I can use my mouse here, but maybe it'll show up on the animation, I'm not sure. And the terms consist of a partition function due to the empty promoter site, to the promoter site with polymerase on it, and to the empty promoter site but with an activator on its bound piece of DNA. Notice that each of these last 2 terms get an energy of a specific energy of each of those proteins to bind to DNA at their specific sites. That is, what that means is that there's extra affinity for those proteins to be at that particular location of DNA. They're essentially, they've evolved to have high affinity at those locations. And the last term is the partition function when both the polymerase and the activator are bound to their respective sites, which gets an energy of specific energy for both proteins and an interaction energy between those proteins. And as we're going to show, you can consider the system as having effective weights for each of those macro states, if you like. And that's what we're going to derive now. Okay, so the calculation starts by finding the probability that polymerase 2 is bound to the promoter site. We write it in terms of the 2 partition functions that have the polymerase bound divided by the total partition function. So we know that each of those partition functions has a combinatorial factor in front of it, which we showed last time we can write in that form shown. Okay, this is then multiplied by a Boltzmann factor, which is shown there, which we can write in terms of a nonspecific energy times e to the minus beta, that should read delta epsilon PD. That's a software glitch. Now note that I've defined the nonspecific binding energy, ENS, in the upper right corner there. So continuing to write out each of the terms as a combinatorial factor times a Boltzmann factor, I finished the numerator and now writing each of the 4 terms in the denominator. Again, a combinatorial factor and the relevant Boltzmann factors. Each term you can see has an e to the minus beta ENS. The last term I'm writing now is the same as the last term in the numerator. And now we see that we can cancel e to the minus beta ENS in every term. And then we can multiply the top and the bottom by that p factorial a factorial over n to the a plus p, as I'm writing here. And that will simplify the expression so that each of the terms can be written as the weights that you saw on the PowerPoint slide. Okay, so now that I've finished writing that, here's another note that, again, we can think of each of those as a weight. So let's define little x equals x over n e to the minus beta delta epsilon xd, where you can see, for example, p would have that definition shown. And this will allow us to write the probability of binding in a simpler way in terms of the small letter symbols that you see there, and epsilon AP. And now we can simplify this still further by dividing the top and the bottom by the numerator itself in the terms in the parentheses there. And this allows us to express the probability of binding as 1 over that quantity in square brackets. Now you can see that the expression can be written as a product of P times a regulatory factor. Let's call it F sub reg, which is a function of the activators present, and it effectively modulates the number of polymerase molecules present, increasing them, in fact, because you can see that for favorable AP binding, F reg is bigger than 1. Okay, and here I'm just writing out the expression for F reg explicitly. Notice that when A is equal to 0, F reg is equal to 1. And you see then we'd be back to unassisted polymerase binding. And you can also see when epsilon AP is equal to 0, that is no interaction between the activator and pol 2, then also F regulatory is equal to 1, and we're back to unassisted polymerase binding. Generally, epsilon AP is going to be less than 0, that is, there's a favorable interaction, and that's going to mean F reg is bigger than 1. And if it's bigger than 1, it means that the effective number P goes to F reg times P. And this effectively rescales the number of polymerase molecules, increasing the number of molecules. We could also put F reg into the exponent, as you can see there in the lower left, and think of it as an effective potential, increasing the free energy of transfer of polymerase into the promoter region. And so then we can re-express the probability of binding using that expression that you see there finally. Okay, now recall that without activators, the probability of binding has the form that is just shown there. So that's the basic form we've seen before. With activators, to recap, the probability of binding has that regulatory factor, which I'm writing out here, and you can see in the plots that the more the binding between the activator and pol 2, the higher the probability of binding. Okay, so now what we can do is we can define an enhancement factor or a fold change, FC, to be the probability of binding when there's an activator present divided by the probability without any activators. So PB of A with activators over PB of 0. And here the fold change is given by that expression in the box, which gives you the enhancement in gene expression due to activators. And here you can see some plots giving the fold change as a function of the number of activator molecules for different AP binding energies. The more the AP binding energies, the more the fold change. And the parameters for the number of polymerase and the transfer energies are given to the right of the plot. Okay, so here's the fold change again, and it's plotted again for two different AP binding energies. And it's an interesting fact that some genes, many genes, can't be expressed without their activating transcription factors, and in fact that's the essence of regulation. So it makes sense to take a weak promoter approximation, where the probability of binding in the absence of an activator is much less than 1. Or p over 1 plus p is much less than 1, meaning p is much less than 1, or 1 over p is much greater than 1. And then the fold change simplifies and becomes fc approximate equals that expression there in the lower right hand side. And if we look at the plots in the upper right, and we plot the exact expression along with the approximate expression for the fold change, there is very good agreement. So this is a very good approximation for typical binding energies that we might encounter. Now the book makes a further approximation, which is to also let the regulated probability of binding be small, or pfreg be much less than 1. In my opinion, this defeats the purpose of freg, and it can be a poor approximation. In this poor approximation limit, the fold change is given by a very simple expression, which is just freg of A. But if you take a look at the behavior of the plots, which are shown in the lower right, you really see that they deviate substantially, only agreeing when the number of activators is about 1. Okay, well, now let's talk about the opposite situation to activation of a gene by an activator. Let's talk about the repression of a gene by a repressor R. So there are 3 situations shown here schematically. Each has its own partition function, each has its own energy. The first situation on the top is that nothing is bound. Neither a polymerase nor a repressor is bound specifically to the promoter or repressor site. That's what that means, though they are bound non-specifically to the DNA. The second situation is where the polymerase is bound. And when it's bound, it gets a transfer energy delta epsilon PD. The third situation on the bottom is when the repressor is bound, and then the polymerase cannot be bound. So they are mutually exclusive. And the weights for these 3 situations are shown to the right there. And the partial partition functions for each scenario are given there as part of the total partition function, and we'll go in and discuss that in detail now. Okay, so now we're going to analyze the mutually exclusive binding of repressors R and polymerase P. We're writing out the partition function, which is 3 terms: nothing bound, the pol2 bound, and the repressor bound. And if the polymerase 2 is bound, it gets a specific energy of binding, and if the repressor is bound, it gets its own specific energy of binding. Okay, and the partition function for nothing specifically bound has the usual combinatorial factor and a nonspecific binding energy, ENS, which has the usual form that we've seen before, but now with P and R binding. Okay, so now we're in a position to write the probability of binding as the ratio of partition functions, where the numerator is the scenario where the polymerase is bound, and the denominator is the total partition function, which has all the partial partition functions added all together. Okay, now from the form of the partition function, you can see that we can write Z of P minus 1 and R when the polymerase is specifically on its specific site, in the form that I'm writing there, which you can simplify as just P over N times the Boltzmann factor times Z of P and R. And so this allows us to write the probability of binding in the above expression all in terms of Z of P and R in every term, which then will allow us to cancel it in every term, leaving a much simpler expression. Okay, so let's do that now. So looking at the expression on the bottom there, we see that we can rewrite that as just PB is equal to P over 1 plus P plus R. Or dividing top and bottom by the numerator gives us the expression that you can see there, which we can write in terms of a regulatory factor. Okay, so here I am just writing it in terms of the regulatory factor that multiplies P. You can see Freg is 1 over 1 plus R. I've written it out in long form there, and you can see that it's less than 1, which means that it's effectively going to reduce the number of pole 2 molecules and reduce the probability of binding.